So this is joint work with my PhD student, Nikolai Gnecco in Geneva, and with Adrian Hitz, Nikolai Mainshausen, and Jonas Peters. So since I guess most of you are not very familiar with extreme value theory, I'd like to start with a short introduction to this topic and then talk about two recent papers. One is more on the modeling side of extreme events, and the other one is how we can detect causes in extreme values. So I'll start with a short introduction. So extreme value statistics or theory is concerned with the analysis of rare phenomena or extreme events, which typically have very small probabilities, but which can have still serious impacts on our health, on the environment, or on the economy. And down here you see three examples that might be these extreme events: flooding, financial crisis, or wildfire. In all these cases, if we are lucky, of course, we have some data. And as a statistician, we'd like to model this data with a model, a statistical model. So this might be the statistical model. But as an extreme value statistician, we're mostly interested in this part of the distribution, so modeling the largest values, the tail of the distribution. You can already see the difficulty here because we only have very few observations that we can actually use to model this tail. And this means we have to rely on an asymptotic theory to come up with justified models for this tail. And there are, of course, this is a univariate example, but there are, of course, multivariate and even spatial generalizations, and I'll come back to this a bit later. So first, let's have a look at a data example that we worked on. This is a river data set in southern Germany. So this is the upper Danube basin. The Danube starts in the Black Forest and then leaves Germany and Passau. And here we have 31 stations where we measure river flow or discharge on a daily basis. And at each of these locations, we might be interested to model the extremes with an extreme value model, this part of the distribution here, because we might be interested for flood protection to know the 100, 200, or 1,000-year return levels. Right? So how large is a 100-year flood? The thing is that, as I said, it's very hard to get from here, I think we have 50 years of data, to get these return levels because we don't have enough data to just empirically estimate these probabilities. So I want to now talk a little bit on how we actually can do this based on extreme value theory. So let's pick out one location and try to model the extremes there. So this is our data, river discharges, and we say we want to estimate a probability that we exceed a high level y. Here y is quite high, so there's just very few observations above. So we cannot simply estimate this empirically. So we can use a trick. So basically we rewrite this probability by Bayes' formula, where we condition now on the fact that x exceeds a moderately high level u. And then we have to multiply with this probability, and here we consider the conditional probability. Okay? So why does this help now? Well, this helps because we can estimate this probability because we have enough data to just count and have an empirical estimate. And for this conditional probability, we actually have an asymptotic theory from extreme value theory that tells us that it can be approximated very well by a generalized Pareto distribution. Okay? And this actually has a simple formula given by this distribution. And basically, it just has two parameters, the shape parameter psi and the scale parameter sigma. So we just have to estimate these two parameters by maximum likelihood, for example, and we get an estimate for our exceedance probability. Okay, the shape parameter psi is the most important parameter here. It tells us how heavy the tail is, so whether we have a Gaussian-like tail or whether we have a heavy tail where we see very extreme observations. So now we can do this for different y's and actually get the whole tail distribution of this river discharge. And by inverting this, we can simply get the return levels now. If we're interested in the 100-year return level, for example, we get a prediction from our model, the blue line here. Of course, the fit is usually not perfect because it's just an approximation, but it's the best thing that we can usually do in these examples. Okay. Let's come back to this map. What we can now actually do at each location that we have, we can estimate, say, the 100-year return level. And this can be used for flood risk assessment. Now, what we can also do, we can parameterize the shape and the scale parameter of the GPD by covariates, such as the catchment size or the altitude. And then we can extrapolate this model to locations where we don't have measurements. And we get actually this hazard map where we have the 100-year return levels even at locations where we don't have a gauging station. Okay, so this is a statistical covariate model. And then we can do this for any kind of return level that we're interested in, 200 years or even higher. But of course, the uncertainty gets larger once we extrapolate further into the tail. Okay, so this is a model if we look at the extremes at one location. But in many applications, we're interested in modeling whether the extremes at two locations, say station 3 and 21, occur at the same time or independently of each other, because for the whole risk, for the whole system, that might be crucial. Right? So we should consider now two locations, station 3 and station 21, and we see that water from 21 eventually flows into station 3. That means there is some strong dependence, or we suspect there's strong dependence, and we also see this in the scatter plot. And now typical questions in multivariate extreme value theory or compound extremes are such that we want to find the probability that the joint exceeding a high return level at the first station and the second station. So these are these different rectangles here. So for example, this rectangle at the top is refers to exceeding the 100-year return level in both variables. And we see there's no data, so again, estimating this empirically is not possible. So we already see that the dependence between the different stations, especially in the extremes, becomes very important because it tells us how much data we have close to the diagonal, or is the data more spread out if we have more independence. So this means, so if we now want to model this, we need a distribution for this bivariate sample. And there are different ways of modeling this. We could, okay, the first thing is just not model it and just count empirically. But then we see, well, starting from a certain return period, we can no longer get the joint return period of joint exceedances. So if we want to have an estimate here, we need a model assumption. We could assume that both variables are completely dependent. So if one is extreme, the other one is always extreme. It's of course unrealistic. This is comonotonicity. Then we just get the same return periods for the joint as for the marginal. We could assume that we have independence between the variables. This is even more unrealistic. As we see, we get completely wrong estimates for the return period because there's actually strong dependence in the extremes of this data. And we can assume something like a normal copula and then get return levels here. But in extremes, we are trying to actually fit models that are optimally adjusted to the extremes of the data and not to the whole distribution, as we did with the GPD in the univariate case, because only like this we can assure that our estimates here are actually well adjusted and have a high accuracy. So how do we do this? Well, here I'll stay a bit high level because otherwise it gets a bit too technical. But basically we have our bivariate sample, and now again we condition on the fact that we exceed a high threshold. But now we have a multivariate sample, so we have to say what this means. And typically what this means is that at least one of the variables exceeds a high threshold u. Okay? Then again, for these exceedances, these threshold exceedances, in the univariate case we had the GPD as an approximation. In the multivariate case, there's a generalization, which is called the multivariate Pareto distribution. And we know then asymptotically that the exceedances, so the blue points, are approximately distributed according to this random variable y, which has a multivariate Pareto distribution. The formula of this y is not so easy as in the univariate case because we have to take account of the dependent structure. But I'll show you a bit later a concrete model that we can use there. Okay, but suppose for now that we have fitted this model, some multivariate Pareto distribution to this blue data. Now, how do we use this to obtain estimates for our threshold exceedances? Well, what we can do if we have a model fit to this data, we can simulate from this model and simulate new extreme events. Okay, so that's what we do here. The gray cloud here of points are new bivariate extreme events. And now we're in a good position because actually we can just count the number of points that fall into these exceedance sets and then get an empirical estimates of that based on the multivariate Pareto distribution. Okay. So if we do this, then here we have a new line for this asymptotically justified model for bivariate extremes. And we can compute the joint return periods for these different sets. And for example, for this set that we exceed in both rivers the 100-year return level at the same time, we get that this happens once in 140 years. Okay? And we can do this now for any combination of stations that we're interested in. Okay, so, but you can see that the impact of different modeling strategies for this bivariate data or bivariate extremes has big impacts on the differences in return periods estimates that we get. Okay, this slide is to show you that for this multi-fit Pareto distributions, we actually have concrete parametric models that we can use. And I'll show you just one model, which is called the Hüssler-Reis distribution, because it's somehow the same as Gaussian distributions, but for extremes. And differently from extremes, it's parameterized not by a covariance matrix, but by a so-called variogram matrix. Doesn't matter so much what this is. It's similar to a covariance matrix, same. But what matters is that we can write down the density of this bivariate or higher dimensional distribution, multi-fit Pareto distribution, explicitly, and it's somehow linked to normal densities. Okay? I'm not showing you this to scare you away from this model, just showing you this to show that there are actual concrete examples where we can just write down the density, and then we can use maximum likelihood methods to estimate this model from our data. Okay, and I'll also show you this because I'll come back to this model a bit later, because this will be important. That actually corresponds to Gaussian distributions for extremes. Okay, I talked about this example of rivers, but more a climate application is in this paper by Jakob Scheichler and Sonja Seneviratne in Science Advances, who looked at the joint hot and dry summers because they facilitate impacts such as insect outbreaks or wildfires. And you can see that in their sample here, you have some dependence between the extremes, and they look at exactly the same exceedance sets, where both variables exceed a high threshold at the same time. And they compare then these exceedance probabilities in a historical climate compared to future climate projections. Okay? I guess you can think in many climate applications, you can think of such problems where you're interested in the extremes, you're interested in compound extremes, where several variables are large at the same time. Okay, this was a short introduction to extreme value statistics in the univariate case and also in the bivariate case. In the first part now, I will talk about how we can go to higher dimensions than 2. Okay, because in the rivers we had 31 stations, not just 2. And in the second part, I'll then talk about how we can assign a causal structure to these events. Okay, so let's come back to this example of river flows. We have 31 stations, as I said, and so we only have a model for 2 dimensions for now. But in this example, we actually would like to do a risk assessment, a flood risk assessment for the whole catchment together. So we'd like to have simulations of extreme events at all of these stations simultaneously, and not only at 2 or 3 stations simultaneously. And in statistics, when we want to go to such high dimensions, and 31 in this example is already quite high, but we can think of much higher dimensional problems, then we need to somehow simplify this probabilistic structure that we have, and we can do this by conditional independence and the notion of sparsity. So we want to have sparse models that somehow simplify the structure. I'll say what this means in a second. And this notion of sparsity and conditional independence links directly to what is called graphical models, or a graphical structure that is underlying our data. And here in this river network, you already see that there's kind of a graphical structure given by the flow connections. Right? I'll come also back to this a bit later. But for now, I want to start in the non-extreme world. So I want to recap what we mean with a graphical model. And the easiest example is if we have Gaussian distributions. So first, we need a graph G. A graph G is just a set of nodes. So here we have 4 nodes and a set of edges that connect these nodes. Here we have just 3 edges. And this is called an undirected graph because we have no arrows that are pointing in any direction. So there are no directions of the edges. And now we want to define what we mean with a Gaussian graphical model. So we need a Gaussian distribution on these 4 nodes. So we have a 4-dimensional Gaussian distribution in this example. And we say that this distribution is a Gaussian graphical model if it satisfies the so-called pairwise Markov property. And the pairwise Markov property means that xi and xj must be conditionally independent given the remaining variables of the graph, if and only if there is no edge between these nodes. So for example, x1 and x3 would be conditionally independent given x2 and x4 because there is no edge between these nodes. And if this holds with respect to a particular graph G, so for example this graph G, then we say X is a Gaussian graphical model with respect to this graph G here. So why is this useful? This is useful because it makes the Gaussian distribution much easier than it is if we don't have this restriction. It actually tells us that the density of the Gaussian distribution factorizes in lower dimensional densities. For example, here it would just be a product of bivariate densities. So basically, we only have to model statistically bivariate distributions and not the whole four-dimensional distribution. Now, if you think about higher dimensions, then this makes the problem much easier because we can just go back to low-dimensional statistical models and don't have to model the whole complex distribution. In Gaussian distributions, it's also very convenient because we can read off what conditional independences we have from the covariance matrix, or more precisely from the inverse covariance matrix, which is called the precision matrix that you see here. If there's a 0 at a location, so at 1, 3, that means that x1 and x3 are conditionally independent given the rest, and that there's no edge, and that's exactly what we see here. Okay, so we have a direct link between the parameters of the Gaussian distribution and the graphical model. Okay, so this is the classical Gaussian world. The Gaussian distributions are not very useful for modeled extremes because they have very weak dependence in the tail. So for extremes or multivariate extremes, we would like to have a different model, and namely these multivariate Pareto distributions, and would like to define what graphical models mean in this framework of multivariate Pareto distributions. Okay, and in this paper with Adrian Hitz, we actually define a new notion of conditional independence for these extreme value distributions. And we denote this by this new symbol with a little e, which means extremal conditional independence. And with this, we can define what we mean with extremal graphical models. Okay, again, we start with a graph, same graph. And we start with a multivariate Pareto distribution. We say that this distribution satisfies the pairwise Markov property now with respect to this newly defined conditional independence, if and only if, well, we have exactly the same thing as before, but just using this new conditional independence. I'm not going to detail how we define this conditional independence for extremes because it's a bit too technical in this short time. But basically, you can think of this as a conditional independence that works for these multivariate Pareto distributions. And then, well, with this definition, it's very natural that we call, if this is satisfied, we call Y an extremal graphical model on the graph G. And then we can show that this also implies that the density factorizes into lower dimensional densities, and we can actually model the lower dimensional distribution instead of the high dimensional distribution. Okay, so this is basically what we do in this paper here. Now, there are very obvious questions for people who work in graphical models to ask. So because in many data, or in most data examples, we don't know the underlying graphical structure. So we have to learn this actually from data. And in order to learn this from data, we have to understand how we can identify conditional independencies in this model. In the Gaussian distribution, we knew we can look at the precision matrix and look at for zeros. For this multivariate Pareto distribution, we have no idea. And actually, for no other distribution, we have an idea. Only for Gaussian distributions, this nice result holds that we look at the precision matrix. For any other distribution class, this is not working so easily. So we would like to have something like this for multivariate Pareto distributions. And then we'd like to have a procedure to learn the graphical structure from the data. So we actually don't need any domain knowledge on the graph. We can just put in our data and gives us back the graphical structure that we then can use for interpretation, for example, and for statistical modeling. We'd also like to have a possibility to enforce sparsity. That means we want to enforce how many edges are in the graph. Okay? We want to have a very sparse graph or a very complex graph. And so we've seen in the normal world, in the non-extreme world, we had to restrict to Gaussian distributions. Now in the extreme world, we restrict to the analogon of Gaussian distributions, namely Hüssler-Reis distributions, which, as I said before, it's a particular class of multivariate Pareto distributions. It's parameterized by this variogram gamma. And based on this variogram gamma, we can actually do a transformation. Doesn't matter so much what this is exactly, but what we get out of this is a certain covariance matrix, sigma k, where k is a particular node that we have to choose. And this covariance matrix and its precision matrix, so just the inverse of it, actually can be shown to encode the conditional independence, but now with this new conditional independence for extremes. Okay, so for the Hüssler-Reis distributions, we can come up with a precision matrix that very simply encodes the conditional independence and very similar to the Gaussian distributions. So this is pretty surprising because, as I said before, we only know for Gaussian distributions how this can be done. And now we have a different model class that is well adapted to extremes, multiple extremes, that actually has the same property. And we can simply, looking at this matrix, find out conditional independence. And that means we can just read off the graphical structure that is underlying this distribution. OK, now once we have this, well, it's a nice result because we can just look at models and find the graphical structure. But we can also use this to estimate the graphical structure from data. So how we usually do this, if we have this result on precision matrices, we somehow want to enforce that we have zeros on the precision matrix. Because if you estimate just empirically the covariance matrix and you invert it, then typically we'll never see a zero because of the uncertainty. Right? So if we enforce that we actually see zeros, and how we do this in statistics is by penalization or regularization. And these are typically, this approach is typically called ridge regression or lasso regression. We use lasso regression because it actually estimates exactly zeros for some entries. And this allows us to enforce sparsity. So what do? We take an empirical estimate of this covariance matrix here, and then we try to estimate a regularized version of it, of the precision matrix. And this can be done by this convex optimization problem, where we have this L1 penalty on the entries of the precision matrix. So for those who haven't seen this before, it doesn't really matter how this complicated problem looks like. What you should take away from this is that we can estimate this precision matrix, and we can enforce that we see zeros on this precision matrix, and we can control with this tuning parameter lambda how many zeros we see. If we have a larger tuning parameter lambda, it means we enforce more zeros, and for the graph, it means we enforce a sparser graph with less edges. Okay, if we leave away this, or if we just put this to zero, then we don't enforce any sparsity. Okay, so we have this tuning parameter to enforce a certain amount of sparsity and to enforce a certain amount of complexity in our underlying graphical structure. Okay, so we know from this previous result that this guy contains the extremal graph structure by just looking at the zeros that we now can enforce with this graphical or extremal graphical lasso problem. Okay, let's come back to the example of this river network. Here we somehow have an underlying natural graph structure, which is just given by the flow connections between these 31 locations, right? Well, this is just a physical graph in a sense. It doesn't tell us whether it's good for statistical modeling or not, right? And let's see what actually happens if we estimate this graph from the data, from the extremes, the extremal observations that we have at these 31 stations. Okay? So we now basically fit a Hüssler-Reis, 31-dimensional Hüssler-Reis distribution, and we enforce sparsity with different degrees of complexity by changing the lambda parameter. So here we take a very small lambda. That means we have many, many edges in this graph. We can now increase this lambda parameter that makes many edges go away. We can further increase it to make the graph even sparser. So the right degree of sparsity in the end we will choose by cross-validation or by AIC, like we usually do in statistics. And now what you can see in this graph, you can nicely interpret it. Well, you basically see the structure of the river, so this physical structure here. But you have additional edges. So what do these additional edges do? Well, if you think of it, the extremes at different locations on the river network are not only caused by the actual physical flow of water, but they are also caused because we see spatial rainfall events that go over the river catchment. Even two locations that are not flow connected can be strongly dependent because the river catchments get similar type of rain at the same time. Right? And these kind of edges in our statistical model introduce this additional dependence coming from these spatial rainfall events. And here we didn't use any background knowledge, any domain knowledge. We just took the data, put it in the algorithm, and we obtain something that is nicely interpretable because here we kind of have a ground truth, which is not really the truth, of this tree structure plus additional edges. Right? So for statistical modeling, we actually see that introducing additional edges is better than just using the graph given by the flow connections. Okay, so what's the takeaway from this first part of my presentation? Well, with these extremographical models, we can do actual risk assessment in quite high-dimensional spaces. And we can use this to simulate extreme events on, for example, this 31-dimensional river network, but also in other situations where we don't have domain knowledge. For example, a network of banks that are interconnected would like to understand the systemic risk in a financial crisis. We can use the underlying graph for an easy interpretation. For practitioners, this can be nice, I think. And this notion of graphical models and conditional independence actually opens the door to do high-dimensional inference and also to do many machine learning techniques that are based on this concept of conditional independence. And we can now start to think of these methods in terms of extreme values. Okay, let's come back to, let's now come to the second part. So as we've learned in Marlene's talk yesterday, dependence does not imply causal structures. And in the second part, we'd like to understand better how we can infer or detect a causal structure explicitly in the extreme events. Okay? So this joint work with Nikolai Gnecco, Nikolai Meinshausen, and Jonas Peters. Okay, so what's the idea here? We'd like to retrieve an information on causality from observational data and would like to use the signal that we see in the extremes. So why is this intuitive? Because on the one hand, well, if we have that a variable x1 causes a variable x2, then we should see this causal link especially strongly in the extremes, because if x1 is extreme, then also x2 will be extreme. Right? So we would like to exploit this intuition. There's also a different perspective on this. We can also think about a causal structure that only holds in the extreme values. So in the bulk of the distribution, we might have some causal structure, but that might change in the extremes, and would like to estimate how this causal structure is between the extreme values. So we don't want to use the information that's in the bulk, but only the information that is in the extremes. So examples why this is important is, for example, for the attribution of climate extremes or meteorological extremes. And I just list here 2 papers. For example, Philippe has worked on this in the statistical community, but I guess also in the climate community, there are a lot of people working on this. Okay, the setup is a bit different from the first part of my talk. The setup is the following, that we have what is called a linear structural causal model or structural equation model, where we start with a graph again, but now it's a directed graph where these directions mean causal effects. So for example, x2 causes x3, x1 causes x3 and x4. And each variable is explained as, in a linear way, as a combination of its parents. So x3, for example, is explained as a linear combination of x2 and x1 plus some noise term. Now, since we're dealing with extremes, and in these river data or other data sets, often we have heavy tails, we're actually interested in the particular case where these noise variables are non-Gaussian, and they are actually heavy-tailed or regular varying. So that means they have a power tail behavior. So these are distributions where we see more extreme values than just in a Gaussian distribution. Okay, so if we just have 2 variables, what are the possible causal configurations? Well, either the 2 are independent, or x1 causes x2, or x2 causes x1. Okay? We can have all of these cases in the same fashion, but with an additional hidden variable that confounds these 2 variables. So that influences both variables that we do not observe, but that we still would like to detect this causal link between x1 and x2. But basically, these are the base cases for causal structures between 2 variables, and we'd like to distinguish between these cases based on observational data. So how can we do this? Well, we define a coefficient that will help us to distinguish between these cases. And we'll define a coefficient that is based only on the extreme observations. So this coefficient we call the causal tail coefficient, denoted by gamma 1, 2, which is given by the expectation of the distribution function of the second variable, evaluated at the second variable, given that the first variable is large. So what does it mean? Let's have a picture for this, that it's easier. So we have the example here that we simulate of x1 just being a noise variable and x2 being x1 plus an independent noise. and that means that x1 causes x2. Okay, this is simulation of this. And now what we do to compute this coefficient, we first fix this u as a high threshold. And then we look at all observations where the first variable exceeds this high threshold. And then we look what happens to the second variable. And we see that then typically the second variable is also large in its quantile function. So that means that if we make this u now more and more extreme, so we send it to 1, the quantile, then actually in the limit we'll get that x2 is always in its upper part of its distribution. So this function here will be close to 1. And in the limit actually we'll get that gamma 1, 2 is 1. Now we inverse the roles of x1 and x2. So we condition on the fact that x2 is large, and we look what happens to x1. Now we see we have a different situation. Actually, we can have x1's, so we condition x2 is large. Now, how can this happen? It can happen from the fact that x1 was large, then we see these points here, or this independent noise was large. And then we actually get observations where x2 is large, but x1 is just like in its normal bulk of the distribution. So in that case, actually, if we compute this limit here, we get that gamma 2, 1 is strictly smaller than 1. So what do we take away from this slide? We take away that we now have an asymmetry between gamma 1, 2 and gamma 2, 1 that helps us to distinguish whether x1 causes x2 or the other way around. And in this case, it means that x1 causes x2. Now we can generalize this. This was the example of x1 causing x2. Actually, we can get results for all of these cases. If they're independent, we have that gamma 1, 2 is equal to gamma 2, 1. They are both 1/2. If, well, just the other way around, then we just switch the roles of these two coefficients. And we actually see that even with a hidden confounder, we still are able to distinguish these three cases. Okay, so this coefficient, this two coefficients, the asymmetry in it allows us to detect the causal direction between these two variables. Okay, and what is important is that we only use the information in the tail, in the extremes. We did not use any information of this data here. We just used the information where at least one of the variables is extreme. So we just used the causal structure. We just estimate a causal structure that holds in the extreme values, but not in the bulk of the distribution. Okay, now in many cases we will have more than two variables. So we have in general have p variables. We'd like to estimate the causal order between these variables. So what we will now do is we compute the causal tail coefficient between all the pairs of the variables and put them into a p times p matrix. So like here. So for example, if we start with a DAG, which gives us a causal order, right? We'd like to estimate from data from this gamma matrix, the causal structure or the causal order in this DAG. So what we do here, we develop an algorithm called the EASE algorithm for extremal ancestral search that will give us, that will take as input this gamma matrix of bivariate causal coefficient, and it hopefully give us as the output the true causal order of the underlying DAG. Okay, what is a causal order? Well, a causal order is a simple summary of the causal structure in this graph. And it means like the true causal order of this DAG has to be such that always if a variable comes before another variable, so if it's parent of this variable, in the causal order this variable has to come before this variable. So for example, x1 has to be before x3 and x4. So this is the case in this causal order. And x2 has to be before x3. Then this is a valid causal order and gives us information about the causal structure. Okay, so now we've defined this algorithm, and actually we can show theoretically that if we put in this matrix of bivariate causal tail coefficient, that then the EASE algorithm returns us a true causal order. Okay, so we can recover the true causal structure just using this bivariate tail coefficients. And this causal structure can now be interpreted as an extremal causal structure because it only uses the extreme values. And the second part of this proposition is that actually even if we have hidden confounders, as we've seen in these examples before, we can recover the true underlying causal structure. And this is quite surprising because many algorithms have a lot of trouble if they are hidden confounders in detecting the causal signal. Okay, so this gamma matrix was defined in a probabilistic way as the limit of these conditional expectations. But in practice, of course, we'd like to estimate this from observational data. Okay, so we have to estimate this causal tail coefficient matrix gamma. So suppose now we have data from two variables and data points, and would like to estimate this gamma matrix gamma 1, 2 and gamma 2, 1. How can we do this? Well, we simply use a non-parametric empirical estimator by fixing a high threshold and then counting in order to compute this conditional expectation. This is an estimator of the true gamma 1, 2, but we can actually show that it is a consistent estimator. And this is what we typically want to know in statistics, that what we're estimating actually will converge to the true value once we get more and more data points. Otherwise, it doesn't make sense as an estimator. Right? So we can show that this is consistent. We need certain assumptions on how we choose our threshold, because we want to choose the threshold so that it goes higher and higher. So we look at more and more extreme events. But at the same time, we want to have enough data points to actually estimate this coefficient. Okay, so we have to be a little bit careful how we choose the number of exceedances in this estimator. Okay, and now this was just the consistency result for one of these coefficients. Now we estimate these coefficients in this big matrix between all these p variables. And what we actually want to know is, based on observational data, can we consistently estimate the causal order? And yes, we can. So this Ease algorithm, when we use it with the estimated matrix gamma, so the estimated causal tail coefficient, then we can show that with probability 1, we get back the true causal order, or with probability 0, we make a mistake in estimating the causal order. Okay, let's come back to this example. This is kind of the recurrent example in this talk. So the river structure. So why is this a nice example for this task? Because we somehow have a ground truth. Right? So what is the ground truth for causality here? Well, if two stations are flow connected, so 8 and 7, I put a lot of water in station 8, then eventually it will flow down to station 7. So if I see an extreme, or if I'm forced to see an extreme at location 8, then I will also see this extreme at station 7. And like this, we can write down the DAG for this river data, which is just a tree here. And yeah, the ground truth basically is then the causal order given by this tree. Okay, so now we will actually restrict to a subset of variables, so these large variables here. And the point is that if two variables are too close, like 7 and 8, then basically the flow there is so similar, there's no way that we can estimate a causal direction between these two variables. So we basically just take one gauging stations per branch or per tributary of this river network. Okay, so for example, here we take 12, 22, 19, and so on. And then we try to take the observational data at these locations. We compute the gamma coefficient with this empirical estimator, and we put it into our Ease algorithm, and it will give us back a causal order. And now the causal order that we get back is this long vector here. And I will assure you, you don't have to check yourself, that this is the true causal order. So for example, if we look at station 7, this has to come before station 22, station 9, and station 12. So if we look here, 7 is here, 9, 22, and 12 are before. So it gives us the true causal order. So maybe an interesting question is that how from this causal order, what actually does it give us? Well, it gives us information on the causal structure. It doesn't give us the DAG. It doesn't give us the directed acyclic graph. But once we have the causal order, it's much easier to get the DAG by just regressing the variables against its parents or against its ancestors. Okay, so this is basically the most difficult step in getting the causal structure. Afterwards, we can do regression methods to actually get back the actual DAG. Okay, so I still have a bit of time, but actually I think I'm almost at the end. So here are some takeaways from the second part. So with this, this estimation of the causal order in extremes, we actually show that we can estimate this causal structure by only looking at extreme events. And well, this is interesting because we can exploit the signal that is in the extremes. And as I said before, often this is actually more visible in the extremes than in the bulk of the distribution. But it also gives us a way to get a causal structure that specifically holds in the extremes. And I'm not sure in climate science, but in finance, you can imagine this situation that you actually have changing causal structures on like in a banking system. If you have daily trading network, that might be very different from a trading or from a risk connections that you have in a financial crisis, where maybe the big players are much more connected than on a daily basis. Now, maybe in climate change, in climate science, you also have these phenomena that the causal direction can change whether you look at extremes or at daily observations, because maybe you have different meteorological phenomena that influence the extremes more than the bulk of the distribution. So we showed that we can, with this ease algorithm, we can get a very fast algorithm. It's based just on empirical estimates. It's very quick to compute, even for large data sets. And we can consistently estimate the causal structure. And very importantly, the results also holds if we have hidden confounders. Of course, if we have many confounders, then we'll lose power of our algorithm. That is typically the case. But if we have a reasonable amount or reasonable strength of confounding, we still get back consistently the causal structure. Okay, here are some references that I cited in this presentation. I'm happy to take questions. Thank you for your attention.
I have many questions, but I just want to ask two of them. So first question would be, like, if you look into the climatology of river runoff models, let's say, river runoff models, let's say, so we kind of have a vague view of how the water flow is. Yeah. So with the networks that you showed, what is the additional information that I get from your...
So in this example of river networks...
So what additional information do you...
So you refer to this causal part of the talk or the dependence modeling?
Both.
Both, okay. Yeah. So for the causal, I would say it's more like a test of methodology, because you know the ground truth, at least if you don't think that there might be other connections. I cannot think of any other causal connections in a river network. So I think this would be more an example to test a methodology where you have a ground truth, which is very important, I think, in statistics. We have another application, which is in finance, where we actually look how the exchange rate of the Swiss franc and the euro influences different Swiss companies. And we can see in shocks of this exchange rate, which actually happens sometimes because the Swiss bank fixes the exchange rate to a certain amount. So there's there are big extreme events. They can see a direct effect on Swiss companies. So this would be more interesting where you discover something new. And I guess maybe in climate change, there are also examples where you can apply this. Now, for the dependence part, you actually get additional information, because getting these additional edges gives you a better statistical model than just using the physical river network.
Second question. So I guess you have a very long time series for your hydrological data.
50 years, yeah.
Yeah, 50 years. So I guess there are a lot of changes that kind of take place. When, like, for example, the change in the land use, land cover, or how do we treat canals. So I'm just wondering, how do these networks kind of incorporate this, some changes which...
So I think so we excluded actually some stations because there were some dams that were built as something that actually have quite strong effect on the extremes. So this certainly should be looked at whether you have stationary or in-stationary data before. So we did some checks before. Now, if you have different times where you know there was a change, then you can actually try to fit the model on these different time frames and see whether you have a change in the network structure. And this will probably give you an interesting interpretation how this change affected the dependence of extremes. But yeah, what you refer to is you should check for stationarity before you apply these methods. Yeah.
That was really cool. Just to make sure I understood, you actually have a spectral algorithm for learning the network structure of this extremal BaseNet?
Yeah, so you have this gamma matrix that you estimate from data, and then we have this algorithm that I didn't show how it works because I didn't have the time, but you can check in the paper. So there's an algorithm that basically goes through this matrix, and out of this matrix it produces a causal order. Yeah, it doesn't produce directly the DAG structure, but as I said, based on this causal order, you can kind of by regression get the DAG structure back.
Okay, so my question is, do you think there could be future work on a graph that has both regular Bayesian dependencies and extremal, just like you can have these causal graphs where the weight would be the time lag? Mm-hmm. Is there a way to mix nodes or edges on extremal variables and regular?
Okay, so you define different variables, one that is extreme and one the same variable but not extreme, and you want to see whether actually the non-extreme might influence an extreme. I think you can think about these situations, yeah. Because in climate science probably you have the situation where an extreme can be caused by another variable that is extreme, but another one that is not necessarily extreme, right?
Well, also if there's some meta parameter like an edge weight that actually is a knob, so you can study quantiles. Mm-hmm. And not just extremes, and then also kind of average, like distributional assumptions that you would have in a BaseNet.
Okay, if you average things, maybe you should be a bit careful what the interpretation of your network in the end is, right?
Yeah.
But yeah, maybe.
And then also, this can all be kernelized, right? Because often in machine learning, it's not that there's a confound, it's that what you're measuring is not exactly what you care about. And so some of these extreme events that are multivariate might be a nonlinear mapping or embedding from the variables that you are measuring.
Yeah.
But I'm assuming that subject to whatever mapping or kernel you apply to all your variables, you can just do the same thing in kernel space.
Yeah, I guess so. This theory is for these linear structural equation models, but I think not straightforward, but an interesting generalization would be to look at nonlinear mappings and maybe using this kernel idea to go to higher dimensional spaces where you get linearity. Then that would be a possibility. Yeah. Thanks.
I have a question.
Yeah, so it was a very nice talk. Actually, I wanted to ask about this parameter for enforcing sparsity, this lambda parameter you said. So you get additional edges. You start from lambda 0 and then from lambda higher values, and you get additional edges additional to the network of river that you already know, right? Yeah. Is there a saturation effect? How do you choose which lambda value you're going to stop, and which edges that you get, are they informative? And how do you, like, do you go
I just mentioned this very shortly. Yeah. This is a difficult problem in general, because you get many different graphs for different lambdas. And the question is, how do you want to use this graph, right? How do you want to use your statistical model? And typically you would like to use it, or in my application, would like to use it to simulate extreme events. So you'd like to have the best statistical model. And the best statistical model in statistics is often measured by, for example, AIC coefficients. And then you could compute the AIC for different lambdas and then take the one that minimizes this. Otherwise, you could probably do some cross-validation. That's what you typically do in Gaussian graphical models. You do cross-validation, or again, also AIC, and look for a minimizer of this function.
Okay, more questions.
Yeah, very nice talk. Thanks a lot. So you mentioned you have some assumptions on using the multivariate Pareto distribution, and then also and other places in your talk regarding the propositions. Could you maybe give an intuition of what these assumptions are? Like, for example, the Pareto distribution, is that kind of, what's the intuition behind it? Is there some physical intuition why this should be a very widespread distribution? Okay, so in the univariate case, it's not a physical intuition, it's a mathematical it's like a central limit theorem basically, where you use normal distribution if you have to average many things. It's similar to this. This is the limit that appears in the univariate case. Now in the multivariate case, things are a little bit more complicated because different scenarios can happen. It can happen that you have asymptotic dependence, so that you actually have extremes that are dependent in a certain way. This is when you use these multivariate Pareto distributions. You can have another scenario where you have asymptotic independence. That means if you look at extremes at different locations, you go higher and higher, then the events become more and more localized. They become more and more independent. So for rainfall, this typically happens.
Okay, because you have different, very localized events that will cause these local extremes, and that will be quite independent of other locations. And then you actually need different models. Okay, so these multiple Pareto distributions are used for the case we have asymptotic dependence, as we typically see in these river networks.
And for the other parts, like the convergence of the gamma coefficient?
So what the assumption are? Yeah. So the assumption here is just I have this, this linear structural equation model, and I have non-Gaussian noise terms which are regularly varying, heavy-tailed. So these are basically the assumptions. And then the way you choose the threshold.
That are regularly varying.
Yeah, so power law tail. Yeah.
Have time for one more question? Okay.
Thanks, very nice talk. So I was wondering for the second part where you estimate the causal order.
Mm-hmm.
Okay, causal order. The threshold that you choose to choose your extreme events will probably change the causal order, right?
Yeah.
It can happen.
Yeah.
So is there a way to maybe look at the stability of the DAG in the end to choose this threshold?
I think this is a good idea, and this is what we do in extremes. We always have this thing where we have to choose a threshold, even in the univariate case. And what we typically look for are ranges of this threshold where we have stability in some sense, right? Stability of the parameter estimates in the GPD, or here we could actually look at stability of the causal order. I think this would be a quite good idea. It's also interesting because you can see how the causal order, if the causal and how it changes, if you change the threshold. So if you have a different causal structure, maybe more in the bulk of the distribution compared to very extreme observations. Yeah.
Can I ask one more?
Yeah, one more question.
Are there ways of regularizing with, let's say, a Laplacian, or because you said that the graph that you get when you stop at lambda 0.19 is maybe a little bit more complete than the ground truth. So maybe there is some additional...
There's no ground truth here.
Yeah. But let's say there is only the spatial order that is the ground truth. Then you have additional information that maybe is relevant, like it rains in a certain area, which makes sense. So I wonder if you regularize with some additional information, the Laplacian or something else, if it helps you get that structure and that additional hidden information.
But now you talk about the dependence, not about causality, right?
Yeah, exactly. Now is the first part.
Okay, so there we don't really care about ordering. We just care about a good statistical model, like a good sparsity graph. And certainly you can use different regularizations if you have additional information on certain regions, for example. I think it would make sense to introduce different regularizations in addition to this sparsity L1 regularization. And you then get certainly different graphs. Like in Lasso, you also have many different ways of regularizing. There's a huge amount of literature on this, how you can do group Lasso or things like this. And I think all this you can also try to use here if you want to include additional information.
Any more questions? Okay, so there are a few announcements, but let's first thank again the speaker.
Thank you.